Okay, why don't we begin today's colloquium? So today's speaker is Manbharat Dhadly, and he currently works at the U.S. Naval Research Laboratory in Washington, and he holds a research assistant professor position at George Mason University. He obtained his PhD in space physics from University of Alaska in Fairbanks in 2015 and worked as a National Research Council postdoc at NRL from 2015 to 2018. And his current and previous research looks at understanding the small-scale and large-scale behavior of the high-latitude thermospheric wind circulation and consequences of the small-scale variability on wind-driven transport. And during his postdoc at NRL, he gained experience in statistical data analysis and tools working on historic and current satellite and ground-based measurements of the upper mesosphere and thermosphere, and fusing them together in coherent ways to study the large-scale response of high latitudes winds to various magnetosphere and solar inputs. And so today he will give a presentation titled Cyclones at the Edge of Space.
All right. Hello everyone, thanks for inviting me here to present a colloquium. And I'm Manbharat Dhadly. I work at Naval Research Lab as a contractor now and hold a research assistant position at George Mason. And my contributing authors are John Emmett and Douglas Drop from Naval Research Lab. And data providers for this talk are Mark Carney, Anasoya Olia, Alco, Gordon Shepard, Chanwu, Dr. Jonathan Makla, Changzup Lee, Genova G, Rick Nick, and Aaron Ridley. Without their contribution, this talk or research was not possible. So the primary focus of my research is to understand the large-scale behavior of high-latitude neutral winds in upper thermosphere. And the title of my talk is related to that, because the title is Cyclones at the Edge of Space, and we have two permanent kind of cyclones at high latitude, one in high latitude thermosphere, one at southern high latitude, another at northern high latitudes. And I'm talking about high latitude neutral wind circulation because the neutral winds at high latitudes are shaped by high latitude electrodynamics in such a way that the resultant neutral circulation looks like winds driven by winds driven by cyclones, like tropospheric cyclones. So, but mechanism of formation of these kind of cyclones in troposphere and high latitude neutral wind circulation is very different, because in troposphere the cyclones are formed by the pressure system, but at high latitude the cyclone kind of this here is formed by the high latitude electrodynamics. So here the figure on the left is one of the examples here. So this is the neutral wind circulation at northern high latitude as a function of latitude and local time for moderate KP conditions. And you can see that the neutral circulation is like a giant eddy. However, it's not a cyclone, but it's an anticyclone because of the direction of the rotation. But it's like a wind driven by a large cyclone. Okay. All right. Yeah. Okay. So that's what I'm going to talk about, the large-scale behavior of high-latitude neutral winds in upper thermosphere. All right. So here's a high-latitude neutral wind circulation, our physical understanding of how the high-latitude winds are driven, what are the primary forces. So this equation governs our current physical understanding of the high-latitude neutral wind circulation. There are four primary forces like pressure gradient, Coriolis force, viscosity, and ion drag. Ion drag is very important at high latitudes and not that much important at lower or equatorial latitudes. So the time interplay between these four forces, or primarily between pressure gradient, Coriolis, and ion drag, shapes the neutral wind in such a way that the neutral wind looks like this at high latitudes. So the figure on the left shows E cross B drifts. So there's a plasma. It's a motion of the plasma at high latitude, and it formed two cells. So if sun is here, this is local. This is noon, midnight, dust side, downside. So there is dust side, downside convection, and dust side convection. Dust side convection and downside convection. Now, if there are no other forces except the ion drag, the neutral winds would follow this kind of motion, but the pressure gradient and Coriolis force shapes the neutral winds in such a way that the neutral wind patterns look like this. And this is the resultant neutral wind circulation at northern high latitudes. So when the winds are driven anti-sunward by the solar pressure gradient, when they cross the pole, they experience high ion drag, and there is splitting of the motion like this on the towards the dust side and downside. However, on the dust side, ion drag and Coriolis force work in the same direction. That's why we get a beautiful circulation pattern here. However, on the downside, the ion drag and Coriolis force work in opposite direction. That's why we have very underdeveloped or non-existent downside circulation. That's why I said it looks like a cyclone here or a giant eddy. So now we know how the high latitude winds are primarily driven. Now the question is, why are we studying high latitude winds? First is because the Earth's most dynamic space weather occur at high latitudes, and magnetosphere dumps a lot of energy and momentum to high latitude thermosphere and ionosphere, and neutral winds are considered the major transport of these perturbed composition or perturbations, and globally redistribute the energy and momentum dumped by magnetosphere at high latitudes. So they are the perturbations that are created by magnetosphere at high latitude can transported by the neutral winds to lower latitude and can create global disturbances in the ionosphere and thermosphere weather by transporting high latitude disturbances composition or energy and momentum. That's why understanding the large scale behavior of neutral winds is very critical for operational space weather applications. Okay, importance of neutral winds. Here is a simple example of large scale transport by the high latitude neutral winds. Here what I have done is taken the horizontal wind model, winds from the horizontal wind model at this altitude, and placed few tracers or air parcels, or you can say balloons, at over Siberia, and traced them forward in time. Where would they go with time? So let's see. You can see they are splitting now. Initially they started as a blob, but now they have split, and now they have moved far distances apart. So the blob that started here is now dispersed over large latitudes and local times. So the main purpose of this this movie is to show that the high latitude neutral winds can transport the whatever occurring at high latitudes to other latitudes like lower and middle latitudes. So for example, magnetosphere is dumping energy at this point. Let's assume that. So within few hours, neutral winds would distribute that energy over hemispheric scales. So that's the importance of neutral winds at large scale. And this is an example of local scale transport by neutral winds. Here I have taken the real observations from Poker Flat and placed few balloon guns or air parcels in the field of view, and let's see where they would go with time. So tracing forward in time. So, I'm sorry. So you can see that it's forming a channel here. All the air parcels or tracers are moving in one channel here. And then a lot of mixing is going on. The sharp gradients occurring here that are not shown in the model because they are large scales.
This is again 400 kilometers.
This is around F region 250. So now a lot of mixing of air parcels is occurring at these scales.
Do you consider vertical movement too?
No, there's no vertical movement. It's just a horizontal. Right. Because the scanning Doppler imagers or FPIs have only few measurements of the vertical wind. Like they measure only at the zenith. All right. So
Do we know whether vertical transport is important?
Yes. Yes, it's very important.
Question mark.
No, it's very important.
It is-
Especially because it has the capability for rearranging the composition.
Right. So we can say that the both large scale and local scale view of the neutral winds is very important for understanding what's going on at high latitude and how the composition or perturbation will be transported to lower latitudes. Now, why are we studying neutral winds after decades of study? Because our current understanding of large scale as well as small scale high latitude neutral wind behaviors and a systematic response to various solar and magnetospheric or heliospheric forces still mainly qualitative and lags corresponding understanding of high latitude or ionospheric dynamics in many ways. This is largely due to historically sparse neutral wind measurements, and unlike ionospheric drift measurements, it's currently not possible to construct an instantaneous picture of the global or regional winds. I will discuss this later or next slide. So no single observational data set can provide comprehensive space-time coverage of high latitude neutral wind system. However, over the past 2 decades, historical observational databases have grown sufficiently to permit a meaningful statistical analysis of at least high latitude average and horizontal winds. Now, I said unlike ionospheric drift measurements, because ionosphere people are kind of very lucky that they have super Dart network like this. Here they have pretty good super Dart network that has coverage, pretty much full coverage at high latitudes, northern hemisphere and southern hemisphere, and that they are getting high spatial and temporal resolution data from super Dart. But neutral wind people are not that lucky because they don't have such extensive network like this. Also, the neutral winds are not available during daytime. They are available only during nighttime. So we can study neutral winds only at nighttime so far. So neutral ionospheric people kind of have a luxury here that neutral wind people don't have. So current state, including present and past observations. So these panels show location of observation of all the current and past ground-based high latitude observatories. So total are 20, 11 in the northern hemisphere, 9 in the southern hemisphere, and it includes all the current as well as past neutral wind measurements. So so at the moment only 11 are operational and others are just a history. So we don't have extensive network as the super Dart, but these are the measurements that we have so far. The space-based measurements that we have from 4 instruments is not shown here. And this is this movie will show you the data accumulation time lapse. So this is a time lapse of data accumulated so far, neutral wind data accumulated so far from 1980 to 2015 at northern high latitudes. The data I have divided into 3 seasonal winds: December solstice, equinox, and June solstice, as a function of latitude and local time. And you can see what data we have so far if we overlap the data in these 3 winds. So we have FPIs on the night side, windy data mostly on the day side, and Gochi data then around 2010 or 2008, SDIs kicked in and Nation Network kicked in. So we have pretty much we have pretty good coverage in the winter time, and during summertime most of the data is from space-based satellite. And if we and this is just this is accumulation of the data. It's not data at single day. It's over this time period, 1980 to 2015. All right, so this is the data distribution we have so far. One important thing here is that the ground-based data, ground-based stations provide only nighttime data because it's very hard to measure neutral winds from ground-based during daytime. So most of the data we have in the daytime is from satellites like Gochi, Windy, or DE2, and we don't have any current observations of daytime data, daytime neutral wind measurements. Okay, empirical modeling. Why are we want to model or build empirical models? As I discussed earlier, that currently it's not possible to construct an instantaneous picture of global or regional wind, and no single observational database or data set provide comprehensive space-time coverage of high latitude neutral wind system. However, in past 2 decades, observational databases have grown sufficiently that we can do something with them and combine them in such a way that we can produce a coherent picture of high latitude neutral winds. Thus, in this case, if we combine all the data sets together, empirical characterization of high latitude wind based on their statistical behavior is an invaluable source here. Also, we know that even though the physics-based models are getting better with time, with the increasing complexity, it's extremely valuable to have tools like data-based climatology that represent the actual data and to test our physical understanding or tune our physical understanding and test the new data sets. So empirical models actually serve as a necessary benchmark to tune our physical understanding and validating the new data sets. So high latitude thermospheric wind model HL2M, this is what my current project is. So I'm working on a high latitude wind model that combines the data sets from all the current and past neutral wind observations that we have and creating a parametric representation of average and neutral winds as a function of day of year, latitude, longitude, local time, geomagnetic activity in magnetic coordinates. Now, why do we care about magnetic coordinates here at high latitude? Because ion drag is one of the primary drivers of high latitude neutral winds, and ion drag or ionospheric motion or plasma motions are better organized in magnetic coordinates than in geographic coordinates. So that's why to better understand the high latitude neutral wind behavior, we would have to use the magnetic coordinates. We already have a horizontal wind model, and it models or models the neutral wind in geographic coordinates. So it's good for middle latitude and equatorial latitude, but at high latitude, horizontal wind model have problems. That's why we are building this new model, and it is based on magnetic coordinates. And the plan is to ingest this model into horizontal wind model to make the horizontal wind model better. And we have already tested one part that if we ingest this model, how the horizontal wind model would behave. It has improved the horizontal wind model a little bit so far, but we are still working on it. So HL2M is based on extensive statistical analysis of long-term thermospheric neutral wind observations from 20 ground-based stations and 4 space-based stations. So in the 20 ground-based stations, we have Fabry-paired interferometers and scanning Doppler imagers. And both at northern and southern high latitudes, 4 space-based instruments are Windy, Gochi, DE2 FBI, and Watts. So in the HL2M formulation, so first we will describe how we combine disparate databases into a coherent picture while overcoming their sampling limitations and if any biases exist among them. For latitudinal and local time dependencies, we have constructed them using vector spherical harmonics. Day of year and longitudinal variations are constructed using simple harmonic functions. Geomagnetic activity dependence is constructed using quadratic B-splines, and quasi-dipole coordinates are used for magnetic coordinate system. Then at the end, I will compare HL2M model winds with the actual data sets that we used in its formulation. So basically, HL2M is a parametric representation of average and neutral winds as a function of latitude, local time, longitude, day of year, KP as a function in magnetic coordinates.
So, excuse me to interrupt, because I don't work in this field. With magnetic coordinate system, is that oriented to with the magnetic pole?
Yes, it's kind of fixed with respect to sun and geomagnetic pole.
I see. I only read in the newspaper that the magnetic pole is kind of wandering.
Right.
So I'm kind of asking myself whether that's a good coordinate system.
So Dr. Arthur Richmond would know this answer because we are using the magnetic formulation developed by Dr. Richmond.
Probably the answer
Right.
is that for a short time scale you can work with that. Is correct.
I don't think we have considered the shifting of magnetic poles in our model. That's a short answer.
Yeah, the movements are fairly small, so definitely less than 1 degree per decade, or actually considerably less than 1 degree per decade for these coordinates.
It was a couple of degrees.
But not lately, right?
But that's pretty
Well,
interesting.
it's on the move. It's pretty exciting. It looks like we're headed for a quadrupole configuration. Sort of a solar max for the Earth.
All right. So Gaussian empirical correction and apparent bias. So in our model, we have used the Gaussian data too because it's a valuable data set, and it is the only data set we have so far that provides full day of year variation in winds at high latitudes. So it's the only data set that has that provides full seasonality in the winds. No other data sets, the data set that has full day of year coverage. So it's the most valuable data set I would say we have so far. And when we were doing our 2017 and 18 paper, we found that the Gaussian winds has bias when we compared Gaussian winds with the other ground-based stations. Now, this is the only data set that has full day of year variation, so we couldn't drop it. We decided to empirically correct it. So what we did, we combined all the data sets that we have together and formed a data climatology, very simple data climatology, and compared it with the Gaussian cross-track winds. And this is what the bias profile in the Gaussian winds look like as a function of latitude. So this is the bias profile as a function of latitude for the northern hemisphere. And as I showed earlier, that the Gaussian winds are mostly covering the dawn and dusk side. So we found that for the northern hemisphere, dawn and dusk side bias profiles were very similar. That's why we averaged them and produced a single curve. However, in the southern high latitudes, dawn and dusk side biases are not of same order. However, they have same structure, but they are different. That's why we decided to keep it different. And in the model formulation, we use the corrected Gaussian data. So this was the only data set that has bias in it. Other than that, all the rest of the data sets were rest of data sets agreed with each other. All right, and this is an example.
Can I ask against which data you corrected?
Uh,
Because dawn and dusk, you have very little data from other measurements.
Right, but if you form like an empirical model from all the data sets together, like you combine windy and ground-based stations.
Ground doesn't give you anything around dawn and dusk. Which?
Just a minute. For example, you have in December solstice, you have pretty good coverage, right? Combine all the seasons together, then you will get pretty good coverage as a function of latitude and local time, and you can.
Yeah, okay. I still don't understand. So for the dawn and dusk, your other data is mainly from windy, and certainly not
Yes,
from ground.
it's from windy. For example, also from the scanning Doppler images. Here you can see scanning Doppler images have full coverage on the dawn and dusk.
Around the same altitude.
No, we combine all the seasons.
Yeah, or the season. I mean, Gaussian is around 250.
Right, it's around
So
250.
is your Doppler scanning also around the same?
Around the same altitudes.
Okay.
So here's the Gaussian corrected versus uncorrected example. Gaussian cross-track winds as a function of latitude for various local time bands and divided into various seasons. Blue curve shows the Gaussian corrected data. The pink curve shows Gaussian uncorrected data, and black curve, the black dots are the windy measurements. As you can see, there is consistent bias between Gaussian actual data and the windy data. And after correction, you can see that the corrected Gaussian data follows the windy data. So there's a pretty significant improvement in the Gaussian that we can use in the model. Right. Okay, after formulating the model, the first step is to validate the model. How the model is performing against the other data sets is we able to capture most discernible trend present in the data? Is the model filling data gaps without adding spurious fluctuations? What trends we see in the data and the model? Now here's the model validation step. Northern high latitude Gochi cross-track winds. The color, various colors shows different ground-based and space-based station. For example, blue is Gochi, DE2, Thule, Resolute Base, Thunderstorm, windy daytime winds, windy nighttime winds, Tulik Field, Poker Flat, Millstone Hill, Longyearbyen, Kirwana, so Dankela, and Model Wind. So I would say that focus only on the blue and the red because I'm showing the Gochi cross-track wind. So comparison with the model makes sense here. So the Gochi cross-track wind as a function of day of year for various latitudes and KP winds, and very different local time winds here. Actually, it's a 33-page comparison. I have shown only here 3 pages of the comparison. So we can see that the blue, which is the Gochi data, and the black, which is the model data, they agree very well. So the model, we think, is working very well within the data resolution. And so yeah, overall model is working very well, and it is able to capture the seasonality as well as the KP dependence of the winds. Seasonality, for example, here, the cross-track winds are a function of day of year. So you can see that there is pretty strong seasonal dependence in the winds that we knew so far, but was not able to confirm it with the data sets. And this is the only data set that has full day of year coverage. And you can see the KP dependence in the winds too. Winds are getting stronger with KP getting stronger. Yes, the other data sets are following what is available in the Gochi, and the model is fitting the other data sets very well. One other important thing we notice here is that the Gochi winds are kind of showing semi-annual variation in the winds, and we have never noticed this before, I think. So there is semi-annual variation present in the Gochi data, and this kind of variation is well known in the density, but it's not been seen before in any of the data sets because we did not have any full day of year coverage before. So this may be real. I think it's real because it's not an artifact due to data correction, because we corrected the data as a function of latitude, not day of year. Also, when I saw this kind of behavior, I also did comparison with the actual data we got from Gochi, and in the actual data, this kind of variation is also present. So is there SAO in winds? Looks like there is, but we are still working on it to. It's a semi-annual variation in the winds. Like if you see here, so this is the day of year variation, and you can see there's semi-annual variation on the top of annual variation in the winds. Right?
Semi-annual, what's the over?
Oscillation.
Oscillation.
Usually we speak of the SAO and the mesosphere, but by extension, you could speak of it in the thermosphere.
Right.
It's one of the great mysteries as to whether it's really the same thing.
Right, but the SAO in thermosphere, like at high latitude, is well known in density.
Sure.
Right. And maybe this kind of SAO in winds may be driven by that variation in the density. We don't know yet. But it is present in the data, and we are working to find why it is there. But that's very interesting. All right. Northern Hemisphere zonal wind comparison between data sets and the model. So 6 data sets here. Thule, quite active. Resolute Bay, quite active. Thunderstorm, Longyearbyen, Tulik Field, and Poker Flat. The blue data points are from scanning Doppler images or Fabry paired interferometers. The green green points are for windy daytime measurements. Red data points are for windy nighttime measurement, and black is the model. So you can see that overall the model is working very well because it's able to capture all the discernible feature or prominent feature that is available in the data. So overall it's working well. However, there are some discrepancies here at Thunderstorm. The model is capturing the overall tone of the data, but not capturing all the variation that's present in the data. we can capture all the variation present in the data by increasing the resolution of the model. But if we increase the resolution in the model will start ringing at other places, like at spurious fluctuations where there is no data. So there's kind of trade-off. We can replicate all the data and then add spurious fluctuation where there's no data, or we can smooth out the data and keep the model kind of limited where there is no data. So overall, it's pretty well working very well. And northern hemisphere again, different stations, zonal winds. This is Kirwana, Sodankela, Millstone Hill, Peach Mountain, and Urbana. Again, we see that the model is following the data very well. One interesting thing here is that at polar latitude, the variation in zonal wind is diurnal. However, at aurora latitude, it becomes semi-diurnal because of the presence of strong ion drag here. And then again, from aurora latitudes to middle latitude, it changes from semi-diurnal to diurnal again. Now, meridional wind comparison. Northern high latitudes again. Again, the same story. Blue are the data from FPIs as SDIs. Green from windy, red from windy night. Green are windy daytime winds, red are windy nighttime winds, and black is the model. As you can see, the model is following the data very well and capture most discernible trend present in the data. However, there are some fluctuations like this that may be the artifacts in the model, but we don't have data here. So we can't say anything about it and can just assume that the model is doing well here. But yeah. Now, meridional wind from different stations, same story continues, that model is doing well. Now, southern high latitudes, zonal wind comparison from Arrival Height, Jangbogo, McMurdo, South Pole, SDI, Mawson, SDI, Haley, Palmer, and Mount John. Again, data points are the same, like blue is from ground-based SDI FPIs, green is windy, and black is the model. Again, the same story, that the model is behaving well wherever there is data, and it's also working well where there is no data. And it's filling the gaps very well without adding any kind of spurious fluctuations that we can expect when there is no data.
It's kind of hard to see everything.
Yeah.
There's so much on there, but does my eye see this and say that it's doing a better job on the FPI data, tracking FPI than the windy?
Yeah, because windy winds are sparse. They're not like, we don't have much data from windy. But there is a lot of data to constrain the model from ground-based SDIs and FPIs. That's why it's working better when there's a lot of data. All right, southern high latitude meridional winds, again, model is doing good. Now, KP dependence of the winds. For this comparison, for one-to-one comparison here, the model was run at the locations of space-time location of the observations, and we plotted this wind. Okay. So for one-to-one comparison, model was run at the location of observations, and here the black is the model and red is the data. So all the data sets were combined to produce this kind of plot. This is just to check if model is able to capture all the variation that is present in the winds when KP changes. So here's a zonal wind as a function of KP for various latitudes, meridional wind as a function of KP for various latitudes, and various local time bands. As you can see, for the northern and southern hemisphere, the KP dependence in the zonal winds is pretty much similar as expected, but meridional winds wind response is opposite. This is because of the sign convention. Otherwise, the KP response in both hemispheres is pretty similar, and the model is able to capture most of the trends that are present in the data. Now here are the polar vector wind plots, longitudinally and seasonally average, northern high latitude, southern high latitudes as a function of local time and latitudes for KP3, 5, and 7. So qualitatively, we can see that the circulation at southern high latitude is kind of very smooth, but here on northern high latitude it's kind of breakage here. And right. So this is just a qualitative view, not a quantitative view, just to give you an idea what interhemispheric differences can exist in the winds at high latitudes. And this is just the UT dependence of the winds, northern high latitude and southern high latitude as a function of, so UT 0, 8, and 16, again UT 0, 8, and 16, KP2, KP5. If we just focus on these two panels, you can see that the winds at UT 0 is different than UT 8. So there is UT dependence on the winds, and that's it. Yeah, there is. Okay, longitudinal dependence in the zonal winds at northern high latitude. Let's just focus on these two panels because there is too much going on. Zonal wind as a function of latitude, local time for various day of year winds, longitude from 0 to 180 and 180 to 360. And you can see that there are very, very small differences between these two panels. So this means the longitudinal variability is very small in the winds at high latitude. However, it is there, like there is subtle differences, but overall they look pretty similar. Similarly, for meridional winds, the longitudinal variability is very small. However, there is variability. Similarly, for zonal at southern high latitude, meridional at southern high latitudes, same story continues. Okay, now what are the limitations of the model that we had developed? First is IMF dependence, and second is F10-7 dependence. We don't have IMF dependence in the winds yet. We don't have F10-7 dependence in the wind yet. And these two variables has shown strong dependence on, like, high latitude winds show strong, I wouldn't say strong on F10-7, but strong dependence on IMF. But we could not develop a parametric representation of IMF yet because there is not enough data that we can divide into multiple winds. The data is already divided into 5 bands like latitude, longitude, local time, KP, and day of year. If we divide data further into these bands, the data will lose the statistical significance. So we could not formulate the IMF dependence and F10-7 dependence in the model yet, but the data from high latitude is coming in, and in future we will be able to do that. Also, we have limited resolution of the model. This is because we don't have enough data to support the fits where we don't have enough data to support the fits. If we increase the model resolution to capture all the variation that we see in the data, the model will start ringing at the location where there is no data, and so it will be hard to constrain the model at the location where there's no data. That's why we have limited resolution, and due to that limited resolution, we cannot include higher order harmonics. As a result, winds look much smoother than the data. So all the limitations have one solution, which is data, and it's not available yet in that quantity we need. Okay, neutral wind network, current versus future outlook. Now, for a comprehensive understanding of neutral winds at high latitude, ion neutral coupling, and how the high latitude disturbances propagate to low latitudes or equatorial latitudes, we need an extensive network of observatories at all the latitude we can. And that can provide us wide geographic coverage. And this is the current situation. We have pretty good coverage over Alaska and good coverage close to East Coast, but this kind of area is empty. Now suppose magnetosphere is dumping a lot of energy here at low latitude, and how would that perturbation, how those perturbations would travel to lower latitudes, we don't know. And models, physics-based models have shown that these perturbations travel to lower latitude and affect the space weather of lower latitudes. But how would those disturbances travel to lower latitudes, we don't know, as we don't have enough data. And this is what we think we will be able to achieve in future, like scanning Doppler images, place them at all latitudes, and FPIs place them at middle latitude, at least on the land. And if some perturbations are going here, we can trace them how they're moving equatorward. All right, now suppose such a extensive network is realized, then what the winds would look like. Here's just a simulation. This is what the winds would look like. But there is a catch here, because currently neutral winds are measured by the ground-based instruments only during nighttime. There is no daytime data. That's why there is a gap here. So even in the future, that daytime data won't be available. And at present, complete local time coverage can only be obtained through climatology. All right, I will stop here and take questions. Yes, sir.
Therese, are data available from CHAMP?
They are, but it's around 400 kilometer, and it's cross-track winds,
Right.
right?
Like Gochi.
Right, Gochi, right? But Gochi is kind of in the down-dust sector. It's very easy to incorporate that data in the model. However, a lot of work should be done in order to include CHAMP in the model, but it's doable. However, for this model, I have limited the data between only 200 and 300 kilometers. Right, and D to Gochi, windy falls in that region, but we can definitely include CHAMP data.
There's probably not too much height variation.
Right. And we don't know how the winds change with the height. I mean, it's assumed that the winds after 250, they stay consistent, but you never know.
In one of your slides, you showed virtually no data or very little data for KP greater than 5. So how reliable or meaningful for your model for KP greater than 5 for the storm case?
Greater than 5?
Yeah. If you go back to one slide, there's virtually no data or very sparse data. Yeah, here.
Right.
Yeah, so
I haven't done detailed comparison after KP greater than 5 because there's not a lot of data, and so I don't know how reliable is the model after KP5. But if you look at this, looks like it is very reliable because these are the data points we have.
that's data you base your model based on this data you develop this model.
Right.
But your data is so little, so I don't know if
Yeah, I mean,
actual
here's the KP dependence in the model, and
yeah, it's
compared
so
to
the
the data.
dependency, yes.
So wherever is the data is following the data.
Yeah,
Right.
yeah, that's true.
That's it.
You think the future icon will add to your effort here?
Icon is limited to only low latitudes. We are looking for GDC mission because that will cover the high latitudes, and there will be multiple satellites, I think.
Those are mostly in situ measurements, is that correct? GDC.
Right.
Would that be a causing problem for your comparison with your remote sensing data set?
Maybe. I thought about it.
Similar to Gochi.
Yeah, another quick question. I remember in John Emmer's early paper regarding windy, you kind of calibrate the Gochi data to windy data. I remember windy data also have a bias. Is that true? I believe in his earlier paper discussed that only the disturbance wind is used for statistical study.
Right, disturbance wind is used because, right, to eliminate if there's any bias in the data.
Yeah.
I agree with that. But when I was doing my 2017 and 18 paper, I did comparison between daytime, like the windy data, with the nighttime data. They pretty follow. They agree with each other. Like there's no jump between daytime and nighttime wind data. So I feel like windy data is pretty good.
You think no bias in windy data? Or there is?
I don't think there's any bias. I would stay on the windy side. Come on, Wendy.
Yeah, so I'm a little unsure of sort of where this stands, because you showed us these extensive plots and you were then saying, oh, this is, the model fits the data satisfactorily, but there were many places where there were discrepancies, and so I would like to know what kind of a criterion you apply on when a fit is significant. I mean, and then at some point you were saying, yes, we could actually model this variation at high latitude, but then we would have some ringing in other areas. That sounds a bit disconcerting.
Right, I mean, that's a
So
problem.
what does it mean?
This means that we need data everywhere in order to constrain the model, which is not available. Right, we can achieve, like, we can replicate the data, as you said, and that will introduce fluctuations at other areas where there is no data, right? So we have to be limited there.
Are there at some juncture principal limitations of the model coming into play, and what are those? Well, the model never is reality, right?
Right,
You
right,
have
right.
made certain assumptions.
Yes.
And so when you talk about this ringing or things like that, what of your assumptions you would feel most uncomfortable about?
Oh, okay. I mean, all of the assumptions that are used in the model, they have been validated. Like, we have modeled the winds based on this criteria, like latitude and local time dependencies are constructed using vector spherical harmonics, and vector spherical harmonics have shown, I mean, using vector spherical harmonics we can replicate the data, and it has been well known. And the day of year and longitudinal variation using simple harmonic function, and this has been shown in the previous papers that yes, it's able to, we can use simple harmonic motion functions to replicate that. And recently a John Emmert paper discusses that the geomagnetic activity can be constructed using quadratic beats of line. So all the mathematical assumptions that we have used here, they have been validated in the past. Okay.
Well, that you can expand this in terms of spherical harmonics and can make a certain approximation then to be able to deal with that. That I will believe right away. I mean, that's goes without saying. But what I'm trying to understand is what physics are you missing with this approach? And why are you certain that that isn't important? Rather than tweaking models and having better and better agreement, I would like to get a feeling on sort of what is the physics that we are struggling with.
It's an empirical model. It doesn't have much physics in it. So it's just a fitting of the data using mathematical functions. So if there is no data, it's hard to fit the data. But the fits wherever there's no data depends on the data above and below it.
Well, the physics, in a way, are determined by your choice of independent variables. For instance, you have chosen to fit in a geomagnetic coordinate system based on your physical understanding of what's going on. You've explored local time dependence because you know from the physics, or suspect from the physics, that that's a really important matter. And then, of course, you have to make choices about how many terms, where to throw away terms, where to ramp them down, and that's based on things like, well, that looks like ringing, that doesn't look physical. So there are choices that are based on physical understanding, even in an empirical model. You could call this a semi-empirical model, similar to HWM or MSIS.
Right. Yes.
Thank you, Stan.
But in the utility to us anyway, or to me, one of the principal utilities is, whenever you have a numerical model, you say, okay, is the numerical model any good? And so you go, well, let's compare with data. And of course, that's a lot of work because there's all these different types of data, and they all have biases, and they all have offsets, and they all have sampling. And so you say, well, let's look at this big storm. You go to one spot, and you compare with the data. You say, look, that looks pretty good. And then, well, or no, that doesn't agree. And what does it tell you? It doesn't tell you. It doesn't give you the answer as to how to fix the model. But this type of climatological formulation, taking into consideration what Wenbin was pointing out, that during very large storms, you may take it with a grain of salt. But for the climatological formulation of quiet to moderate to slightly moderately disturbed conditions, it seems like that would be a very valuable thing to be able to compare the global climatological response of an empirical thing to a numerical model, just as we use MSIS to find out if we're on the right page, knowing that MSIS is imperfect, but if you can at least get close to MSIS, and you feel like you've got some of the biases out. So how would you approach that? I mean, there's so many different coordinates. There's the longitudinal, the UT, the solar time, the latitude, the time, the activity level, solar activity, which you're not covering.
Right.
How do you begin to approach? Finally, I'm getting to a question here. How would you approach comparing this type of empirical model to a numerical model, with the eye towards improving the numerical model?
I think that's less of the issue for the empirical models, isn't it? I mean, you use the empirical model. One, it's interpolating.
Yeah.
And two, for given inputs, it's a predictor.
Yeah, but
Independent
both models know everything about the entire globe all the time. So you solved all those sampling problems that are difficult for numerical modelers to deal with. But so then what do you do?
So basically, empirical models are the representation of the data, the actual representation of the data, right? And the physics-based models are based on our physical understanding what is driving the winds, right? So if some terms are missing in our physical understanding, we can learn from the empirical model. Right? If we can include some terms in the model that fixes the physics-based model and matches the winds with the empirical model, maybe that's the term we are missing.
So maybe just make all those plots that you just made, except with the numerical model, and overplot them.
Right.
And then develop a model that fits it, and you
Well,
have an empirical model of a physical model.
Well, no, you could do that, and make all those plots, and you'll see discrepancies. So somehow you have to have a methodology for understanding how to interpret those discrepancies.
There are still many new spots. I agree with that.
Having this in mind, in our community, actually the term empirical model has moved towards semi-empirical model, and I think that would be maybe a more appropriate term. You were showing this dream scenario, how you could sort of track everything if you would distribute like 5,000 radars all over the North American continent. What would be the justification? Why is this important to follow this into that detail?
So it has been shown that the neutral winds transport the high latitude fluctuations to lower latitudes and disturb their space weather, right? So we need to understand how they travel. We don't know if if they're coming from high latitude or they're in situ or something. If you can trace that, yes, they're coming from high latitude is the culprit, but maybe they're not coming from high latitudes, right? But so far we don't know what's going on where there's no data. That's why if we can realize such a big network, we can trace those fluctuations going to low latitude, or maybe they're not all it.
But did I understand correctly that still it isn't clear to what extent the picture changes when the vertical exchange is being fully tracked?
I'm sorry, repeat.
There was when you described the horizontal scenario, I asked this question, what about the vertical exchanges? And I understood they are not in this model right now.
Right, even in the horizontal wind model that has been extensively used, there is no vertical motion is not considered. Because we don't have many vertical wind measurements.
So could we be fooled by the, sort of a flat Earth scenario where the 3D guys do change things all the time?
Well,
It's make it more complicated, that's all.
well, vertical winds are much smaller.
Right.
We know that.
Horizontal,
So if, for instance, you wanted something to drive an ionospheric model or to understand ionospheric motions, we don't think that the vertical winds per se are distorting the ionosphere in the same way that the horizontal winds are. But if you were trying to develop an understanding of composition changes, which are driven by vertical motions,
right.
you would not use a formulation like this other than perhaps to drive a conservative system that inferred neutral winds from the general circulation,
Right.
which is what drives the vertical winds, of course.
Yeah, and isn't it that because of the huge change in density in the vertical profile, that even small winds could change your mass balance quite a bit?
They do change the mass balance.
Yes.
Are you going to plug in your model into HWM?
Yes, we are planning to include this in SWM because that was the basic purpose of this model, to improve the working of our sampling model. And we have already tried one case, and it has significantly, I would say, improved the Highlatitude winds in the horizontal wind model. Because, yes.
All right, is there no more questions? Thank you again.
VSH
Yeah.
models, we can do that. You give it, you can take model output and do his fitting thing.
Yeah.
VSH.
I shouldn't take this home with me.